Hi, my name is Galen Tunnicliffe, and today I'll be presenting Lab 5, Magnetic Braking with Faraday. Quick lab overview. The purpose of this lab was to collect experimental data of a bar magnet falling through multiple conducting rings which make up a tube. We created a computational model which replicates this interaction of the magnet and conductive tube, and this allowed us to see the interactive forces at work as the magnet falls through the tube. We then compared this experimental data to the computational model's produced data. So, lab procedures. Of course, we're using Faraday's law and Savant's law. So we observed that if we had a ferrous tube, the magnet would have just stuck to the sides and not fallen through, so it wouldn't work for this experiment. So we used the phone magnometer app to find and label the north pole of the bar magnet. We dropped the bar magnet north pole first in the roll of aluminum foil for 5 trials. We recorded the video and created a computational model of the magnet and aluminum interacting. So we got our experimental data from that. The magnet seemed to fall at constant velocity once it entered the tube, not with the normal downward acceleration of gravity, so it falls slower than in free space. So this calculated 0.686 seconds, difference due to the possible inaccuracies from Lab 3 calculation of mu, since this is a computational model. Okay, so we go into the coding section. Step 1 is just to enter the values for the tube measurements. Step 2 is creating the magnetic field function due to the bar magnet dipole. Step 3 is calculating the change in flux function using flux equals the integral of B dot dA, where we found B earlier. And then step 4 is finding the current of the ring, which equals the change in flux over the resistance. We need to find the force of the magnetic field of the magnet on a ring in step 5 and 6. And then we use Newton's third law, which means this is the same as the force of a ring on the magnet. We enter in gravitational force, Newton's second law, to sum the forces, iterating functions of velocity and position that update as the magnet falls down to the tube to give us instantaneous values for the graph. So our computational model looks like this. The model shows the relationship between the induced magnetic field, flux, and current, and the magnetic force of a single slice of tube. Added up all the magnetic force on the slices to get the magnetic force on the tube, which must equal the magnetic force on the magnet. So this is a little graph of the velocity versus time, so you can see where the magnet enters and exits the tube. So, quick discussion. If we have the dynamics of the system would change when we flip the magnet around. No, they wouldn't, because the induced magnetic dipole in the tube would flip as well, so the force would just be the opposite. How does the total time in tube of your neural load system compare to that of the computational system? So the computational model value is 0.686 seconds, and the experimental value is 1.19 seconds. So real life has factors like air resistance, so an extra force that is in the F net equation could help account for this. The shape of velocity versus time plot tells us that the forces are pretty much equal inside the tube, so velocity is constant, but then after we exit, it's only gravity. Questions: what if the resistivity of the conductor were reduced as close as possible to 0? Since induced current is inversely proportional to resistivity, induced current would increase, so this means the magnetic force on the magnet would increase, so the magnet would fall slower. And if there were holes or slots cut into the tube, the induced current would decrease because we have less rings, essentially. Okay, that's the end of my presentation. Thank you.